Hey guys, welcome back to Anatomy and Physiology. So today we're going to start Chapter 2, the chemical basis of life. Now, before I really get into this, I want to say the following. I'm not quite sure how much I'm going to put in this video. I'm trying to decide how long I want to make the videos, and man, this is 40 some odd slides. We're going to cut a lot of it out, but still 40 some odd slides. And we're just going to have to play it by ear, and I'm going to try to keep the videos under an hour. We'll see. We'll see how it pans out. Alright, let's roll. Alright, so a couple of concepts before we go any further, and that is matter and energy. Now, this is very straightforward. Matter is anything that occupies space and has mass. Okay, this pointing device I have is matter. This TV is matter. Okay. Energy is only a tangible effect. The only way you know of its existence is its capacity to augment matter, to change matter, to do things with it. Okay, it's a, quote, capacity to do work, to put matter into motion. Now, energy is very important for us here in anatomy and physiology. There are two formats that are worthy of our mention here, being kinetic energy and potential energy. Kinetic energy being directly involved in doing something, and then potential energy being a storage. Boy, does this echo throughout the rest of this class. All right, a couple of terms: chemical energy, electrical energy, mechanical energy, and radiant or electromagnetic energy, and how these all kind of fit together. Let's go here. What we have is, one, chemical energy. Okay, chemical energy is a storage that would be potential. Okay, it's a form of potential energy. Chemical energy is a storage of energy, like the fat in your system, the carbohydrates in your system. These are all energy storage. Okay, they are energy storage that you can then use to do things with your metabolism. You probably have heard of ATP at this stage, I hope. ATP is an energy storage molecule. It's chemical energy. Okay, it is chemical energy that can then be used to do other things. Now, there's also electrical energy. Electrical energy is a flow of charged particles. All right, a flow of charged particles, much like your nervous system is a flow of charged particles. All right, the whole way your nervous system works is by changing sodium and potassium levels all throughout the length of a tube, basically. That is electrical energy in the grand scheme of things. Every time you think and do something, move, it's all basically electrical energy. To be frank, that's the whole plot of the Matrix movies, okay, is that we create electrical energy. Alright, mechanical energy, that which is directly involved in doing work, like flexing our muscles to pedal a bicycle, for example. And then there is, of course, radiant or electromagnetic energy, which is that which travels in waves. Now, this is, in essence, light. Okay, this is basically light, and we release radiant or electromagnetic energy. Think about like infrared. Okay, heat, your heat signature, that is going to be releasing radiant or electromagnetic energy in the form of heat, and thus we do display it. So energy is very, very important for us, and how it works and what it does. Worthy of mention, I suppose, is the law of conservation of energy, and that is that energy is neither created nor destroyed, it simply changes form. Okay, let me say that again. Energy is neither created nor destroyed, it simply changes form. Now, what the heck does this mean for us? When you eat a hamburger, that's energy. You're getting energy from this. Does all the energy from that hamburger go into your daily activities and routine? No, of course not. You lose a lot of it. Okay, a lot of it is dissipated as heat. In fact, you probably realize this. If you get up from where you're sitting and leave the room where you're at and go out into an open area and run a lap around whatever building it is you're at, when you come back in, you're going to feel hot. And the reason you feel hot is because all that muscle flexion generates heat. Okay? The energy in your system, changing from a storage, a potential energy, to kinetic, energy of motion, walking, moving, running, causes a little bit of loss of heat. Okay? A little bit of loss of heat. It's worthy. Good enough for us. And the comment here is that you got energy coming in, electrical energy coming in, turning into radiant energy, and if you grab that light bulb, it's going to feel warm. So there's a little bit of loss of heat. So energy is neither created nor destroyed. It simply changes form. Good. All right, atoms, ions, and molecules. Now, we have played this game before, but I'm going to play it again for you. You know that you are an organism. made up of many organ systems. Those organ systems made up of individual organs. Organs made up of 2 or more different tissues. Tissues made up of groups of the same cell working together. Cells made up of different organelles. Organelles being made up of big old honking macromolecules like DNA shown here. These big macromolecules being made up of smaller molecules like water molecules shown here. At the base of this are atoms. Now, this is very, very important for us, alright? Atoms. This is where we have to start, because if you're going to understand all the rest of this, you really need to understand how atoms function. Okay, so we're going to start at the bottom, we're going to work our way up. Uh-oh, technical difficulties. Something's happening here. Okay. Alright, good enough. Alright, all matter is composed of elements. Now, there are 6 basic elements that make up the vast majority of our body. These are oxygen, carbon, hydrogen, nitrogen, calcium, and phosphorus. Now, oxygen and hydrogen should be pretty obvious to you. Why would these make up, 75% of your body by mass? Because what are you mostly made of? You're mostly made of water. Okay, so if you're mostly made of water, and water's chemical formula is H2O, that means that you are mostly hydrogen and oxygen. Okay, mostly hydrogen and oxygen. You're water-based. Then there is, of course, carbon. So, if you've ever watched some good sci-fi movies, you may have caught people saying that you're a carbon-based life form. Fact. All of your proteins, your carbohydrates, your lipids, your nucleic acids, any of the big hydrocarbons, these are all big honking molecules. Like, when I see you, all I see is protein. Like your skin, your hair, your nails, your eyes, your optic muscles, oh boy, muscles, all of that. All of that, it's all carbon-based, okay? Carbon forms these big old long chains, and different other atoms will bind to this, mostly hydrogen in most cases, and oxygen for that matter. But all of these big long carbon chains make all of your large molecules, like your proteins, your nucleic acids, your lipids. All of that is carbon-based, so that makes sense that there'd be a lot of carbon in our system. Nitrogen I'm not so worried about. Calcium and phosphorus are pretty obvious. These are going to be in your bones, so you obviously would have a lot of calcium and phosphorus by mass. Alright, all elements are composed of atoms. Now these atoms are composed of subatomic particles. Okay, these are these subatomic particles, the protons, neutrons, and electrons. And I predict that the next slide is a discussion on protons, neutrons, and electrons. Yeah, I'm sure I'm going to get into this later. I'm just going to lay a bunch of this on you now and hope for the best. Okay, let me just tell you about protons, neutrons, and electrons, and we'll just sort of go from there. Alright, first things first. Let's talk about charges. Okay, protons display a positive charge, electrons display a negative charge, neutrons are neutral. Okay, protons positively charged, electrons negatively charged, neutrons are neutral. And in nature, all atoms tend to be electrically balanced. And what that means is, if I've got 5 positively charged protons, how many negatively charged electrons do I need to be balanced? An additional 5, okay? So 5 and 5. In other words, 5 positively charged protons, 5 negatively charged electrons. We see this over and over and over again. It's very easy to predict the number of electrons just by knowing the number of protons. It's a straightforward process. Now, neutrons, on the other hand, are neutral. They have no charge at all. What makes protons and neutrons special, though, is that they are heavy. They have mass. Okay, they have a weight to them. We say that they weigh 1 atomic mass unit each. Okay, so protons and neutrons have mass, and because they have mass, think about this like a gravitational thing. They attract one another and hold together in the core of an atom called the nucleus. So what we have here is a Bohr model of an atom, and in the central core here, we have protons and neutrons. Okay? Protons and neutrons, because they have mass, they hold together in the core. The electrons are virtually weightless, so they're just flying around in clouds, or electron clouds, on the outside of this atom. Now, so make sure we're together. Protons display a positive charge. Let me try again. Protons display a positive charge. Electrons display a negative charge. Protons and neutrons have mass, thus they are found in the central core of the atom called the nucleus. Electrons fly around the outside at extraordinary speed because they are virtually weightless. They're just held in place basically by the positively charged protons and the internal charges therein. So if an atom is going to come together with another atom and do some sort of chemical bonding, what subatomic particles, matter. The ones on the outside, the electrons. Okay, the electrons are going to be the drivers, if you will, of what we call reactivity. Now, I probably just did 5 slides in one, but I feel like I got most of what you need to you. Let's just see what happens. Atoms are electrically neutral. That means they have the same number of protons as electrons. That is a fact. You can see this here, 6 protons, 6 electrons, 1 proton, 1 electron, 7 protons, 7 electrons. Yeah, man. Yeah, that's how that works. They are electrically neutral. That's a fact. We have a entry from the periodic table here. The entries on the periodic table look as follows. There is a atomic number, a symbol, and a mass number. Let me make sure this is the correct slide for this. Yeah, okay. Atomic number and mass number. Let's go ahead and talk about these. The atomic number at the top here, 2, small number, is just the number of protons. So if helium has an atomic number of 2, that tells you it's got 2 protons. And if helium is electrically balanced in nature, if it's got 2 protons, how many electrons does it have to have? 2. Very simple. Okay, very, very simple. The atomic mass, on the other hand, is the total weight of the atom. So how much does it weigh in total? Helium weighs 4 atomic mass units. So if helium weighs 4 atomic mass units, this tells you quite clearly that there is a certain number of neutrons in place to give it that mass. Now, if the atomic number is 2, and protons weigh 1 atomic mass unit each, that's 2 atomic mass units, and the total mass is 4, then how many neutrons must there be? Okay, 2 plus 2 is 4. Okay, so you know that there are 4 atomic mass units in there, 2 of them are protons, so 2 of them have to be neutrons. Perfect. Perfect. Atomic mass, yeah, okay. I'm pretty happy with all that. Let's just leave it where it lies. Alright, so when matter combines, they do so through interactions with electrons. They do so through interactions with electrons. And in the world of chemical bonding, the bondings that we will talk about involve what's called ionic bonds, covalent bonds, of which there are 2 formats, and then last but not least, hydrogen bonding. Now, let me explain something real quick. Hydrogen bonding is a side effect of covalent bonding. Okay? Hydrogen bonding is in fact a side effect of covalent bonding. So let's kind of ignore that one for the time being. We're going to come back to it and talk about it at length. Hydrogen bonding is so important, man. Like, the whole reason you exist right now is as a result of hydrogen bonding. It's very, very important. Basically holds all of our major molecules together in their unique shapes. Chemical bonds are energy relationships between electrons. Now, I'm not going to go into a whole bunch of detail here. There are classes you can take that you will probably be taking that will teach you all about this. I'm going to keep it very simple because it's an anatomy class and you need to know the basics just so that you can move forward. Now, what I first want to point out is that electrons are indeed found in energy shells on the outer surface of these atoms. These energy shells, the outermost of which, will be called a valence shell. The valence shell, the outermost energy shell, is going to be the energy shell which allows for an atom to bond or chemically attract other atoms. Okay? Now, in the realm of valence shells, or just energy shells overall, the first energy shell of an atom can contain a maximum of 2 electrons. Okay, a max of 2 electrons. If it's got 2 electrons in its first energy shell, it is happy. The next energy shell, the second one, can have a maximum of 8 electrons in it. Okay, 8 electrons. And if it gets to 8 electrons, then it is happy. And we go no further. Okay, we're going to go no further. We're going to keep this very simple. For example, down here is carbon. Carbon has 6 protons, 6 neutrons, so its atomic mass would be 12. Its atomic number would be 6 for those 6 protons. How many electrons must it have if it has 6 protons? Well, it's going to have 6 electrons. Count them. 1, 2, 3, 4, 5, 6. 6 electrons. Now, how many electrons can that first energy shell house? 2. 1, 2. Now, how many are left over? Okay, 1, 2, 3, 4 in the second energy shell. How many more electrons does carbon need to be happy? Well, it needs to have 8 in its valence shell, the outer shell, so it needs 4 more electrons. Rewind it, listen again, and let's go through and do a million examples. Alright, here we go. Here's helium. Alright, helium and neon are considered noble gases. They are called noble gases because they are basically non-reactive. Okay, they are in fact non-reactive. Helium has 2 electrons total, 1, 2, and that fills its first valence shell and it's completely satisfied. It does not chemically bond. Here is neon. Neon has 2 electrons in its first energy shell and 8 in its second energy shell. If neon has a full valence shell here at 8, it's chemically stable, it's non-reactive. But what about the rest of these? Here we've got hydrogen. It's only got 1 electron. Needs 1 more to be happy, to have a 2 total in its valence shell. Here's carbon, as we talked about. It's got 1, 2, 3, 4 electrons in its valence shell. It needs 8 total to be happy, so an additional 4. Here is oxygen. Oxygen has 1, 2, 3, 4, 5, 6 electrons in its valence shell. How many more does it need to be happy? An additional 2, for a total of 8. That is how this works. For these atoms to become stable and happy with one another, they have to get a full valence shell through chemical bonding. And when we say chemical bonding, let me say again, we're talking about electron relationships here, and the 2 major groups that we're going to do are the ionic bonds and, of course, the covalents. Here we go. Ionic bonding. Ionic bonding is a situation where there is a transfer, a thieving away of an electron from one atom, and it becomes permanently a member of a different atom. Okay? They are stolen off. So a perfect example of this is sodium and chlorine. When sodium and chlorine come together, that makes sodium chloride. And sodium chloride you should know about because that is good old-fashioned table salt. Okay, table salt. Now, these 2 atoms by themselves are terrifying. Sodium is a alkali, all right? This thing in air, it's a metal, but it will melt, and if placed in water, it'll oxidize very exothermically and basically burn and explode, okay? It's not anything you want in your system. Then there's chlorine. Chlorine was used as a chemical warfare agent for years. They would hurl bombs of this stuff into opposing trench lines in World War I. The folks would inhale the chlorine gas. It would bind to the water in their lungs and form hydrogen chloride, HCl, hydrochloric acid, okay, and it would burn their lungs from the inside out and kill them. This stuff's terrifying. But you ionically bind these 2 together, sodium to chlorine, to make sodium chloride, and you make table salt. It's delicious, okay? So how does this happen? The idea is this. Sodium has 2 electrons in its first shell, 8 in its second shell, and then it has a third shell with 1 lonely electron, which is weakly held in place because it's literally just flying around on the outside. Okay? Just flying around on the outside. And then there is chlorine. Chlorine has a pile of electrons, and it just needs 1 more. It needs 1 more to be chemically stable, to have a full valence shell. So what do you think happens? Chlorine wants that electron real bad. Sodium doesn't mind if it lets it go. So the electron leaves sodium permanently and is transferred permanently to chlorine. But here, folks, we got a problem. Because what's the charge on an electron? Electrons are negatively charged. So if electrons are negatively charged, that means that a negative charge leaves sodium and attaches to chlorine. Ergo, chlorine's overall charge becomes negative. If sodium lost a negatively charged electron and it was electrically balanced beforehand, then now it has more protons than electrons. So what happens to sodium? Sodium takes on an overall charge of being positive. It becomes what's referred to as a cation. Chlorine becomes what's referred to as an anion. This is sodium chloride because one is positively charged and the adjacent one is negatively charged. These 2 attract like magnets. They just kind of stick together. It's a very weak attraction. You can put sodium chloride in water and the two will break up like crazy because water is a wonderful, what's referred to as a polar solvent. Okay, it's really good at breaking up positive and negative relationships like this. Sodium is easily busted up in water. Sodium chloride is easily busted up in water because this is a weak attraction, but an attraction all the same. An ionic bond. It is an ionic bond because these are now ions. They have weird charges. Okay? That is our first and most simplistic chemical bond. And then we get into the covalent bonds. Now, in the realm of covalent bonds, there are two. The first we'll talk about is a non-polar covalent bond. All right, a non-polar covalent bond. What's happening here is very straightforward. What we'll have is a variety of atoms binding to an adjacent atom by sharing their electrons. Covalent. The electrons are shared. And this is non-polar covalent. What that means is that the electrons are shared equally. Those electrons spend an equal amount of time around the carbon as they do around the hydrogens. All of the atoms have equal visitation rights, okay? They are going to share those electrons perfectly with one another, resulting in molecules which are quite symmetrical and display no visible charges. They are nonpolar. They display no charge. Compared to polar covalency. In polar covalency, what we have is one part, or one atom you might say, displaying what's referred to as electronegativity. Okay? What will happen here is the electrons are going to be shared in a polar covalent bond, but the electrons are going to spend the predominant amount of their time around one part of the atom and not the other. The electrons, in the case of water, love the oxygen. So they spend all their time around that oxygen. Okay? Because the electrons spend all their time over here against the oxygen, that gives the oxygen side of this molecule, a bit of a negative charge. Not a whole lot. It's not terribly crazy, but a little bit of a negative charge. And because the electrons are always up here, giving a negative charge to this side, that means that the hydrogen side of this water molecule display a mild positive charge. Okay, a mild positive charge. So electrons being negative, and they're spending all their time over here, they give this side of the molecule a little bit of a negative charge. So this side becomes mildly positive. That is polar covalency in a nutshell, where the electrons spend more time on one side than the other, so the whole molecule displays a bit of a charge variation. And because the whole freaking thing displays a bit of a charge variation, that gives polar covalently bonded molecules some unique properties. Unique properties. This, folks, is super important. Those unique properties involve the concept of hydrogen bonds. Because each of these water molecules are polar covalently bonded to one another, this means that they attract one another. They display a weak attraction. These weak attractions are called hydrogen bonds. Your DNA molecules are held together, their main structures of the DNA molecules are held together by covalent bonds. A lot of polar covalencies. You know that crazy twisted ladder shape of DNA we call the double helix? You've heard of this? The double helix, that weird shape, that's hydrogen bonding holding that together. Like the individual strands, that's all covalencies. But they're polar. So the unique shape, those are hydrogen bonds. Proteins, like your enzymes in your gut that allow you to digest food, the amino acids that make up your proteins, they're all covalently bonded together. But there are a lot of polar covalencies in there. So the weird shapes that enzymes take on to be able to be functional, that's all hydrogen bonding. No hydrogen bonds, no DNA. No hydrogen bonds, no enzymes, no hemoglobin, no general protein structure. This is really, really important. And not only to DNA and proteins, but also important in the way that it works with you, because you are mostly water. If you are mostly water, that means that you display the basic characteristics of water. And water has unique characteristics because of hydrogen bonding. Think about it. These atoms attract one another and hold to each other. They have an intermolecular force holding them together. So they display some unique characteristics as a result. For instance, here, this is a water strider. This is an insect, a hemipteran. And it's actually capable of standing on the tension generated between water molecules. Like, you can see this quite clearly. I can dip my finger in my water glass here. You see it? There's like a little bubble of water on the end of my finger. That little bubble of water, the molecules inside of that, they don't want to fall off my finger necessarily. I have to do work to get them off of there because the water sticks to my finger and the water molecules stick to each other because of hydrogen bonding. Hydrogen bonding. Good. So with that in mind, I believe it's biochemistry time. Okay, so in the realm of biochemistry, there are two main concepts that we need to discuss. These are the inorganic molecules and the organic molecules. Inorganic molecules are those which do not contain carbon, things like salts and acids and bases. Now they can contain carbon, like carbon dioxide, for example, is an inorganic molecule, but the trick is that inorganic molecules tend to be really tiny. Like a big inorganic molecule, maybe 5, 6, 7 atoms. Okay? A small organic molecule might be hundreds of atoms. Okay? Inorganic molecules tend to be incredibly small and non-carbon containing. Organic molecules tend to be incredibly large and they always contain carbon. Organic molecules contain carbon. These are like proteins, carbs, lipids, and nucleic acids. Alright, so let's go through and talk about some of these, shall we? Water is the most important inorganic compound by a long shot. Because you are mostly made of water, your cells are about 60 to 80% water. That means that the unique characteristics of water reflect your unique characteristics. Again, remember, water hydrogen bonds, and because water hydrogen bonds with itself, the water molecules, that means that there's some weird characteristics that are also reflected in you. So these are really important. Let's go through and talk about them. Water has a high heat capacity. Water has a high heat capacity. What that means is that it takes a lot of energy to really change the temperature of water. Okay, and you know this, you've tried to boil water before, you sat there and stared at it for an absolute eternity. When this happens, well hang on, let me go back further. In essence, because the water molecules are attracted so tightly together, they don't change the way they move very easily. So you got to put a lot of heat into them to really augment their temperature. And because you are mostly water, what this means is that you can go out on a freaking bright and shiny day and your core temperature is not going to change very quickly at all because you're mostly water. Or alternatively, when it's freezing cold outside, you can grab your trash and run out there in a pair of shorts and put your trash outside and you're not going to die of hypothermia. Because it takes a lot of temperature variation or a lot of heat loss, you might say, for your core temperature to change. Yeah, that'll do. Water has a high heat of vaporization. Now, what this means is that it takes a lot of energy to change water's general state. So from a liquid to a gas, to boil water takes a massive quantity of heat. And that's good for you too, because you cool yourself evaporatively. When you get really hot, you sweat. And when you sweat, that sweat boils off your system constantly. Or at least it's supposed to when you're not living in a sauna like Alabama. Okay? It's supposed to boil away. And as it boils away, it liberates huge quantities of heat from your system and cools you down. Don't believe me? Go jump in a pool. In the heat of July, jump in a pool. And when you get out of that pool, when you start toweling off, you're going to feel like you're freezing to death. Because all that water is boiling off your system, and it's liberating massive quantities of heat from you. Highly reactive, so water participates in what are called hydrolysis reactions and dehydration synthesis reactions. Hydrolysis reactions include all of your digestive process. Okay, anytime your digestive process is breaking something down, you're breaking it down through hydrolysis. That literally means hydrolysis, to destroy with water. All of your assemblage, your synthesis reactions in your body, they are dehydration synthesis. You will build new proteins by removing water from amino acids and sticking them together. Okay? That is dehydration synthesis. Hydrolysis is breaking things down. Dehydration synthesis is building things back up. All of your digestive reactions are hydrolysis reactions. all of your synthesis reactions are dehydration synthesis reactions. That is to say that water is incredibly important in the way that your body functions. And water is also a polar solvent, which we discussed previously, so I'm not going to do that again. All right, let's go here. Acids and bases. So in the realm of acids and bases, these are all going to be inorganic molecules. You know they're inorganic because they're small and typically do not contain carbon. All right, acids are considered proton donors. They release, they're electrolytes. They release hydrogen ions when you place them in solution. You can actually see this boil away in certain circumstances that I'm not going to get into here. Yeah, so those are acids. Acids are, well, hang on, we'll talk about pH in a second. And then there are bases. Bases are proton acceptors. They are going to release what are called hydroxyl ions, OH groups. Hydroxyl ions, when placed in solution, your body uses both acids and bases constantly for general function. All right, let's have some examples. So you know that you have stomach acid, that's hydrochloric acid in your gut. It helps you break down food. It helps to activate certain enzymes. You also have a buffering system in your blood that is going to keep your blood mildly basic. So your blood's going to be around like a 7.4 or something in that neighborhood, just so your blood has oxygen carrying capacity. If it gets off of that by too much, you're going to lose oxygen carrying capacity and die. It's a bad way to go. All right, so we use both acids and bases in our bodies to keep us functional. And we measure acidity and basicity, or what I might call acidity and alkalinity. To be basic is to be alkaline, using what's referred to as a pH scale. This is a scale that runs from 0 to 14, and 7 in the middle is considered neutral. That's good old-fashioned distilled water, completely neutral. What do we want to say here? Alright, so I just realized that I've got a magnet on this pointer. I don't really need to be touching that to my TV. Alright, when you are at 7, as you move towards 0, you're becoming more acidic. A pH of like 2 or 3, that's around where your stomach is. That is super acidic, folks. Super acidic. At 7, as you move towards 14, you become more basic. Okay, you become more alkaline. Like ammonia-based cleaners are going to be alkaline. All right. Yeah. So 7 is neutral. Towards 0 is acidic. Towards 14 is basic. And this scale is actually logarithmic. Now, what do I mean by that? A log scale runs on factors of 10. So a pH of 6 is 10 times more acidic than a pH of 7. A pH of 3 is 10 times more acidic than a pH of 4. In other words, these numbers are incredibly different from one another. So when I say that your blood is mildly basic, around a 7.4, what that's really saying is that your blood is pretty basic in reality. Okay, it's pretty basic. Alright, that'll work. I think that'll work. Okay, cool beans. Let's go here. 2 organic molecules. Alright, I am inclined to stop this video here. Okay, let's stop this video here, and I will shoot a separate video for organic molecules, because I don't want to make these too long. I want you to kind of be able to truck through them without having to try to remember where you're at. So let's stop it here, and we'll do organic molecules next time through. Thanks, guys.